thank you very much to all for coming to this conference. From Professor Heike Hofmann from Iowa State University. The conference today will be human-computer interaction. So I will leave the microphones to Johan van Horebeek from CIMAT and Professor Heike.
Good afternoon, all of you. It's really a pleasure to introduce the speaker of today, Professor Heike Hofmann. She's currently professor in the Department of Statistics at Iowa State University, and she's also a faculty member of the Bioinformatics and Computational Biology and Human-Computer Interaction program. She earned a PhD in statistics at the University of Augsburg about 20 years ago. She's a fellow of the American Statistical Association. Her research interests are related to statistical graphics, exploratory data analysis, visual inference, visualization of large data, and statistical computing. She also contributed to the development of several visualization softwares, and many of us, we used it for teaching, for our work, for instance, GJobi, and many R libraries. So it's really a pleasure to have a talk today by her. Moreover, I think it might be an excellent moment to give seminars, because about half an hour ago, at many places in the world, WhatsApp, Facebook went down, so there is no distraction anymore. We can focus just 100% on this talk. It was not part of the plan, but perhaps it's a good coincidence. Please, Professor Hofmann, go ahead.
Thanks, Johan. Thanks, Ricardo, for the invitation. It's my pleasure to be here. Buenas tardes, everybody. So I will start sharing my screen. So this talk is about, and more specifically, it's about how to draw inference from visualizations. So this is joint work with Susan Vanderplas, who is an assistant professor at the University of Nebraska-Lincoln, with Diane Cook, who is at Monash, and Christian Rutger, who is in the math department here at Iowa State. So I'll give a couple of examples of where we use the lineup, talk a little bit about the lineup protocol, and then I'll move into how we can actually draw inference in the lineup protocol. So let's just have a look at why we need graphics. So obviously, I think we can all agree that graphics are essential tools for data exploration. But then when it comes to publishing results, a lot of reviewers, a lot of editors will ask, so what's the p-value of that? And that gets into this discussion of post hoc inferential results, which are obviously not a great choice. And then a lot of people who are doing exploratory data analysis are accused of data fishing, data trawling, data snooping. I think we've all seen incidences of that. Let me just go into the chat. I see that there's a question in the chat. Okay. How do I get there? There we go. I'm not sure that I can. Okay. So yeah. So questions at the end. Actually, I'd be also happy to answer questions throughout in case there are immediate questions that come up. Okay. So So obviously we don't want to be accused of data fishing, and maybe more importantly, we also don't want to do data fishing or p-value fishing, p-value hacking. I'm sure that you've heard those kind of terms. So what we need is we need to find a way to assess the significance of a visual finding. So here is an example at the top. You can see this map, and this is actually a really, really old map. And at the moment, strangely current map by Dr. John Snow from 1854. What's being shown is a piece of London So this would be corresponding to Soho. And when you have a look at the street map of Soho at the moment, you can actually overlay that to this area between Regent Street and Oxford Street. So in August 1854, there was a cholera outbreak in London. And at the time, it wasn't completely clear how cholera was being transmitted. So the foul air of London was thought of as a problem. And John Snow thought that cholera was actually a disease in the water. So he suspected a water transmission, but didn't have enough proof. So what he did was to go through the neighborhood. So he exposed himself to the foul air of London and visited each one of the families and all households that had suffered a death from cholera. And he denoted these deaths by a dot. So each one of these dots on this map is a death from cholera. And then he also put the water sources of the time. So there was no running water in any of the apartments or houses. Instead, people were going to water pumps, pumping water from there and bringing it back home. So he denoted the water pumps with those crosses, and I've marked them with little blue crosses. And you might be able to see that most of these dots are centered around one cross in the middle. That cross is in Broad Street. That's the pump in Broad Street. So he presented this map to the city officials, and they reacted. So you can think in terms of action based on some quantifiable data. So the city officials took off the handle from the pump, and within a couple of days, the cholera epidemic was being stopped. So there were not a lot of new cases, and the epidemic petered out. And when he was trying to provide this map as evidence for cholera being a waterborne disease, the editors of the RSS were actually asking, what's the p-value of this? So what's the p-value of this finding? And eventually, a couple of years later, Dr. Snow actually managed to publish this paper. What he did was essentially a Trelawney triangulation, showing that there was a lot more evidence beyond a hypothesis that there was no relationship between the pump and the places of death compared to what the data is actually showing. So what's the p-value? How can we use the graphical finding directly to quantify the significance of a result? So for that, we've been looking at a protocol that allows us to test a chart in a graphical setting. So that takes this form here. So we show people charts like this with 20 charts in there, and we ask them, which of these panels look the most different? So we're not going to tell them anything else. We're not showing scales because we don't want to bias people with the context of the data. We're just asking people, which panel is the most different? And in this setting, I hope that you agree with me that number 13 looks a bit different from the rest. We showed this to, I think, 23 participants. 20 of them identified number 13 as the most different, and the data is actually shown in panel number 13. All of the other densities are created by just permutating the label that assigns the red and the blue, which means that we're breaking the relationship or we're breaking any obvious relationship, but we keep the margins. And you can see that overall the margins here are the same, but the densities for red and blue are quite different. So 20 out of 23 people identified number 13 as the most different. That seems like the data plot is not, does not agree with these other plots. So that should be some evidence that we can say that the data is a bit different, that there is actually a relationship between the group assignment and or there is a, and whichever value we're showing on the x-axis. So another question. Quite often we've got QQ plots and we're trying to check for normality. So given this QQ plot, can we say, is this normal? And I think we can all agree that there are obvious deviations from a normality assumption, particularly if this region in light gray in the background is supposed to show a confidence interval. So yeah, probably there are some deviations. Now the question is, are these actually terrible deviations? So what we did here is we sampled from a hierarchical model, we sampled residuals after refitting the same hierarchical structure. And these are the residuals that we got from the refit. The data is here in panel number 10. I've already shown the data to you, so maybe you recognize the little hook at the top. We did not show the data panel to our evaluators, so they weren't biased. And none of 68 participants identified number 10 as being the most different. So what does that mean? That means that probably this residual plot shows some deviation from a normal distribution, but based on a hierarchical linear model with a normal assumption, these deviations aren't terrible enough to not be considered from a normal distribution originally. Because in a hierarchical model, we only have asymptotic normality. And obviously here, there's some deviation from normality just given by the model specification and the number of classes that we've got in there and the number of cases, so that we have some deviations. And you can see that in some cases, the normal approximation is actually already holding, and in other situations, in other resamples, in other samples, there's quite strong deviations from the normal distribution still. So here, with 0 participants saying that number 10 is the most different, we probably have some good evidence that maybe the deviation isn't as tragic as we originally thought it might be. So let's have another look at another plot. I'm not going to go into yet what the data is behind. You might guess that with the blue and the red, it has something to do with US elections. But the question is, which of these panels is the most different? And the data is actually in spot number 13. And when we showed this to 72 people, 12 participants identified number 13 as the most different. And now it becomes actually a good question to ask, is this a significant finding or not? Because if everybody agrees one way or the other, 0 or almost everybody, we don't need to get to any kind of significances. But here we are in a place where it's harder to specify whether this is a significant finding or not. So how can we calculate significance based on these lineups? So let me back up for a moment and talk a bit about the lineup protocol in general, and then construct a lineup based on this example. So in mathematical inference, statistical inference, we start out with a hypothesis. We've got our test statistic. We've got a null distribution for this test statistic, given that the null hypothesis is true. And then we reject our test, our null hypothesis, if what we've observed in the test statistic is more extreme than a certain threshold. So we do something similar when we are in visual inference. What's different is how we're declaring the null distribution. So you can think of the visualization of the data as a test statistic. A test statistic usually is just a single number, but there's really nothing written why a test statistic can't be a visualization. A visualization is nothing but a summary of the underlying data. It's just not expressed in a quantifiable or as a quantity. So in the classical setting, we've got a null distribution. In the visual setting, we need to have a way to generate new data where we know that the null distribution is fulfilled. We call those null data, and we visualize the null data in the same way that we visualize the test data, or the data to be tested. So the actually observed data. So here we've got a scatter plot in X and Y, and we're drawing a smooth line showing the trend between X and Y. So here we've got 20 panels overall. 19 are taken by the null plot, by null data. One is we're inserting the test statistic, so our observed data plot, somewhere in this lineup. And then we have people looking at this. If the evaluator is actually able to identify the data, that means that the data is different from the null plots generated under the null hypothesis. And that is evidence that speaks against the null hypothesis. So we now have a way of actually showing people visualizations. And there's different ways of actually administering this lineup protocol. So overall, there's different scenarios, but the scenario that I want to focus on is assume that we're showing the same lineup to k independent participants. So not people in a single room, but k independent participants. So then we want to say that x is the number of times out of these k evaluations that an observer picked the actual data plot. So x is the number of times that the data plot was picked. That means that we can then quantify a visual p-value as the probability that there's at least x number of data identifications, assuming that the null hypothesis is true. So null hypothesis is the data plot is consistent with the null plots generated under the null hypothesis. So that leads us to this, this lineup here. And the way that we've created this lineup is to first take our data plot. This is a plot called the electoral building. It's results from the 2012 US election. Blue means Democratic states, red means Republican states. And then, just as now, the question was, how bad were the polls just before the election, and are the election results really in line with what the polls were saying ahead of time? So that gives us a way to generate null plots. Our null hypothesis is the election outcome is consistent with the polling results. And that gives us a way to create null data. We just sample from one pollster's predictions using their sampling margins of error, and that gives us these data plots for these null plots. Then we're inserting the data plot into one space of this lineup. And if the data is indistinguishable from the null, that means that the election results are consistent with the poll. So a significant finding would tell us these pollsters' predictions were really off in some way. And now we've got these evaluations. So we want to have a probability for at least 12 out of 72 people picked this data plot. What's the probability for that? So we can think of this lineup as, or we can think of the number of evaluations as being sampled from a multinomial distributions. So PI would be the probability that somebody picked panel number I in this plot. So that means that the overall probabilities sum up to 1, so they live on a simplex. And we can say that without loss of generality, we'll just assume that the last plot in the panel was the data plot. So PM would be the probability that we picked, somebody picks the data plot when being shown this lineup. So the question is, what's the distribution of these, of the number of data plots under the null? We know that it follows a binomial distribution with K evaluation, but what is the value for PM? If we can assume that all of these plots are indistinguishable, then it's just a random pick. So one out of those 20, 1 over M for all of these plots. So what do we get when we evaluate this? So the p-value for x is greater than or equal to 12 is very small, 0.00023. So what we're saying here is that a plot like the plot in number 13 only happens in about 2 out of 1,000 cases. Well, that doesn't seem to be true. That sort of fails the sniff test. Because when we're looking at this, 8 seems to be very similar to 13. 4 actually is the only one that has red on top. Number 11 is pretty similar to number 13. So this p-value seems to be too small. So the problem is, if we could assume that all of these plots were the same, we can assume that the probability for PI is 1 over M. But what we see in practice is that these null plots are all a bit different, and some null plots attract a lot of votes, whereas other null plots are really very boring and don't attract any votes. So on top of that, the probability to pick the data plot depends on the probabilities of all of these other null plots because they are on a simplex. So we've got some dependency. If we pick another plot, we don't pick the data plot. So this probability to pick the data plot also depends on the actual lineup. So how do we deal with that? What we see in practice here, I've broken down the 72 evaluations to what actually happened, which plots were picked. And you can see that there's 2 plots, number 4 and number 8, that attracted at least as many votes as this data plot. And you can also see that there's a couple of plots that didn't attract any votes. So the distribution for the null plot picks is very different from a uniform distribution. So what do we do instead? Let's do a small excursion into something called the Dirichlet distribution. So the Dirichlet distribution is a distribution that's on the simplex. So here we've got x1 through xm, or you can think of p1 through pm as the probability to pick a certain plot from a lineup of size m. So all of these xi's or pi's sum up to 1. And essentially we've got xi to the power of some alpha, and then everything's normalized by the beta function. That's the density of the Dirichlet. So how does that work? The Dirichlet has this concentration parameter alpha, and we'll just make an assumption that all of these alpha i's here are all the same. So we'll just assume that alpha I is constant. And when we do that, you can see what happens just on a S2 simplex in the middle of this so each one of these triangles is visualizing the S2 simplex. And we're looking at P1, P2, and P3. They add up to 1. And when we're sampling from a Dirichlet distribution with alpha equals 1, we end up in the middle. So all of those points are all equally likely. So that's a uniform distribution on the simplex. So every combination of P1, P2, P3 is equally likely. If we increase alpha, we go into the center of that simplex. If we decrease alpha to a small value, we go more into the corners. So alpha is called the concentration parameter because it determines how concentrated the density distribution is. And we can go essentially from everywhere from the corners, all of the mass on the corners to all of the mass in the middle of that triangle. So when we increase alpha massively, you can see how this distribution contracts. And for alpha going to infinity, all of those p's are actually going into the same value, which means that they're all 1 over m, or here 1 over 3. So the Dirichlet distribution asymptotically goes to a uniform distribution for alpha going to infinity. Similarly, when we reduce values for alpha, we go into something that looks like here. So what I've done here is sampled from a Dirichlet distribution with a parameter of alpha of 0.05. I sorted all of the probabilities because if you think of those probabilities as the value to pick a particular panel, it doesn't really matter which panel we pick. We're just interested in how many votes won the most attractive panel gets. So if alpha is 0.05, we can see that the most attractive panel gets more than half of the votes. The second most attractive gets about a quarter of the votes. And then the last 25% are essentially for the next 2 or 3, and then nobody else gets votes. So the Dirichlet distribution becomes very sparse as soon as alpha is relatively small. And you can see how this goes. Oh, this was 0.1. So this is a little bit bigger, and then 0.01 means that essentially just 1 or 2 different panels are being picked, and everything, none of the other panels get any votes. So we can now define or assume that the null distribution for our lineup can be assumed to be a Dirichlet distribution with some parameter alpha. And that means that we've now shifted our problem from being not very practical with the binomial distribution to a problem of how do we estimate this rate parameter alpha. Now, alpha can be estimated using a maximum likelihood estimator. So here we've got a maximum likelihood estimator. So alpha hat solves this di-gamma expression. Di-gamma is the derivative of the gamma distribution. So essentially, we're summing over all of the picks for the for a lineup. And the problem that we have is, remember that some of these panels didn't get any picks. So if we're trying to estimate alpha by first estimating these picking probabilities, PI, even if we have 70 to 100 evaluations, sometimes those the estimates for PI would still be 0. So the problem is log of Pij is not stable. And even if we set some very, very small lower limit to the PIs, that's still hugely influential in what the value for alpha hat will be, and it will hugely influence our downstream analysis. So what do we do instead? We can use a graphical solution and have a look at a property of the distribution that depends on alpha. So what we're showing here is how many panels are being picked in 30 evaluations. So each of these dots corresponds to a simulated lineup under a certain Dirichlet distribution alpha. So we're simulating a lineup, and we simulate 30 evaluations. So under the null hypothesis of Dirichlet distribution alpha equals 0.1, 1, 10, a certain fixed value, how many panels were selected? So you can see how these dots generally follow the blue line. And we are, we can now define so-called Z interestingness. So we call a panel in a lineup C interesting if it was picked by at least C observers in K evaluations. And we call this number of how often this plot was picked as ZC. The nice thing is with a Dirichlet distribution and the corresponding beta function, we can actually evaluate this expected value. So the expected value for the number of C interesting plots given a certain rate for alpha is this expression. And while this expression looks really unwieldy, we can use it to estimate alpha. Which means that we can now have a look at how many people picked certain plots in our lineup and use those numbers to estimate alpha. So in this case here, if we just look at the null panel, so that's just the light gray panels, and count, there's 13 null panels that were picked at least once, and 9 null panels were picked at least twice. So if we just use these 9 null panels and we draw the line of expected values, so this blue line is the expected value for the number of 2 interesting panels, so panels that were picked at least twice when there's 60 evaluations. So I'm getting to 60 evaluations because we had 72 evaluations. 12 of these evaluations picked the data plot, so that leaves us with 60 null evaluations. So out of those 60 null evaluations, there were 9 panels that were picked at least twice, which gives us an interval for alpha somewhere between 0.3 and 0.7. So if we now evaluate the probability that X, the number of data plots, is at least 12, we get to a p-value of 0.08. And so A, it's vastly different than the binomial distribution, and B, it's also from a statistical point really disappointing because now we've lost the significance. So if we now tie this back to our original question, are the pollster's predictions significantly different from the election outcome? Not really anymore, but there's definitely some indication that maybe something, that the pollsters were maybe a bit off. So 0.08, there's some indication that maybe there was something wrong with those predictions, but based on this evidence, we can't find it. And from a statistical point, that might be not as satisfying, but from the point of using visual inference as a way to quantify a graphical finding, I'm a lot more happy with this result because this is much more in line with what we're actually seeing. So there's some evidence there. 13 is picked 12 times, but 2 other lineups were picked as often as this. So maybe it's not a particularly spectacular outcome here. So this, the visual inference is implemented as an R package. It's called V-Inference, available from GitHub. And it's ready to use out of the box. So you would need to specify the lineup, outcomes, so the number of evaluations, the size of the lineup, the number of the null plots, and then it will suggest an alpha as well as a p-value. So this approach to using Dirichlet distributions for the null distribution seems to work in practice. We've just published a paper with Stat on how to calculate the Dirichlet distribution and how to estimate the concentration parameter. The concentration parameter gives the Dirichlet distribution really a lot of power and a lot of choices in terms of the distribution, from a completely uniform distribution to a very, very skewed distribution that favors only a couple of null plots. And that's really also reflected in the difficulty of lineups. We've seen lineups where there were a couple of null plots that just looked strange for various reasons. And people then also picked these null plots in evaluations also for various reasons. And in terms of a practical approach that seems to gel very well between practice and the theoretical model underneath. What's a bit weird is a case where something happens like I showed you initially, like 20 people out of 23 picked the data plot. That leaves us only 3 values, 3 evaluations to estimate alpha. So if we've got a very, very strong signal for the data, there's almost no data left to estimate alpha. And we're in a strange situation that we can't get to a significance value when there's a very strong signal, because we can't properly estimate the concentration parameter. In those situations, it might be good to also estimate alpha separately and show to people a separate plot, a so-called Rorschach, that only shows null plots, so that we can get a better handle on how, what kind of alpha to use in these situations. When we actually show null plots like this or null lineups like this to people, what we've seen in practice is that people complain because these lineups without a data plot are very hard, and people get a bit frustrated when they see these, when they are asked to find the plot that's the most different, and really nothing is that different. So that makes lineups harder. But generally, I would like to give these lineups to you and consider them as a way to get p-values when we've got visual findings. These kind of lineups are also good. So I'm not trying to supplant regular statistics and regular tests. I really want to have a complement to that. So when there's situations where our conventional methods break down, there might still be graphics. For example, when you're thinking about what Dr. Snow did with the geographical, with the spatial, with a spatial example, how would we, there's really not a immediate test that we can run in order to measure the p-value for that. So it's useful in those situations where the conventional methods break down. What's also interesting is that lineups allow us to ask participants why they chose a particular plot. So that gives us some insight to visual reasoning. And that's also a really good moment to revive other types of errors. So if you remember type 3 and type 4 errors, so picking the right plot but for the wrong reason, are also errors that we should keep in mind. So for example, having a lineup that has a where we pick the data plot for a property that has nothing to do with the data itself, that's definitely not going to lead to a valid statistical conclusion. So asking for why helps us also to get an idea of which graphical feature our participants, our evaluators use to identify this plot as special. So that's it from me. Thank you so very much. I'd be happy to take any questions now.
Okay, thanks a lot. Well, we mentioned it only through the chat session. If you have any question, please write it down in the chat, because general public does not have access to use voice. So please write it down. In the meanwhile, well, I have actually a very general question, and it's related to what you were mentioning at the very end. So you have your slide where you make the comparison between the visual approach and the traditional approach. You take as a starting point in both approaches that you know your test statistics. And that's of course related with the errors you mentioned at the end, no? So my question is a little bit about how to generate null plots. So I understand in some situations you just have the data, but in all situations you will simulate them under the null hypothesis, but probably you have many ways to do that, and some will be more efficient than others. So can you comment a little bit about that aspect?
Yeah, that's an excellent question. Yes, generating nulls is really a crucial piece in here. We need to generate null data in a way that doesn't immediately give away the data plot. So what we're often doing is we use permutations. So if there's multivariate data involved, it's relatively easy to use permutation of just one variable so that we keep the margins intact. So we don't rely on the margins of the other variables that are involved, but we break any kind of relationship between X and Y, say. What we're also, but that only works when we're in a situation that where we've got at least two variables. Oftentimes we have some distributional assumptions. So for example, in the case with the normal model, we actually, or with the normal QQ plot, we actually had a hierarchical model in the background. So we were able to simulate from that, assuming that our normality is actually fulfilled and then refitting. Sometimes we are dealing with very large databases and our data is only based on a sample, so then we can resample from that data to produce more and use that as a way to generate new plots. But sometimes we also run into structural issues. So for example, when you think of the map of Dr. Jon Snow, we've got X and Y. If we just resample X and Y, these dots, and we're not careful, then this is not at all lined up with the street map of London. And at that point, it just looks odd. And everybody will recognize the data just based on this strange layout. So resampling in the presence of actual other structure is very tricky.
Okay, good. We got a set of questions. You can see them in the question and answer bottom at the end. But if you want, I can read them. One question is, have you identified niche areas in which these techniques works well, whereas traditional ones don't?
Yeah, so one of our first papers actually addressed that. In a really simple situation, we were looking at the example of essentially what happens when we're violating one of the assumptions for a t-test, and we have different sample sizes and different variances. So we're violating homogeneity. The t-test is not robust to that. When we show box plots, those are very robust to that. So essentially, we can use robust approaches, or we're maybe more used to using robust approaches when we visualize. And as humans, we're very good at just discarding things that just happens a couple times. So we're very good at disregarding unimportant information from important information. So yes, this scenario of violating homogeneity, the lineup didn't lose a lot of power, whereas the t-statistic lost power quite rapidly.
Okay, thanks. Another question. Is there a way to determine a good number of null plots? So many might be overwhelming and only a few might be not enough to draw conclusions.
You guys are really good, yes. So that's a really good question. The only reason that we used m equals 20 is assuming that we just pick a plot by chance. We've got a 1 in 20 chance of picking the data plot. So 1 in 20 is 0.05. That's usually our significance level for statistical tests. So that's why we used 20 originally, but if the plot is more complicated, that's 20 plots. Evaluating 20 plots is a huge load on the observer. So it's just cognitively hard. That's when we go down to 12 or sometimes 16 plots. But it's a good question and none that we have really evaluated. In practice, we can. So if we use now the Dirichlet distribution, we can just evaluate power and but in practice, going below 12 plots, we need to increase the number of participants to a degree where Amazon is getting a lot of money from us.
Okay. Slightly related to that question, how sensible could be the methodology to different visualization methods, from those that plot data directly to those that plot a projection of multidimensional data?
Yes, so one of the real strong suits of the lineup is that it gives us a way to evaluate visualizations themselves. So, and that's very similar to power of test statistics. Some test statistics, if we say, okay, we've got the sample and I want to estimate mu, the mean of that, and I'm using that with the minimum, that's a terrible test statistic. And it loses a lot of power and it's very biased. When we have a terrible chart, we'll also see that people don't have a good way of picking out the data. So we can visualize the same data in different ways, add null plots in the same ways to the lineup. And then just compare which of these lineups results in the most data identifications, assuming that we can average across the participants' abilities. We can assume that those didn't matter. We can say that the lineup that showed the most data identification was the one that had the best design for visualizing this data set. So it allows us a way to also assign a certain power to data plots.
Okay. And last question that I see here, it's about the use of this approach for georeference data, data on maps, a little bit similar perhaps to what you were showing at the very beginning.
Yeah, georeference data is hard. Yeah, so it depends on us having a really good grasp of the structure in the background. And if you do have the georeference data, there might be a good way to simulate from within those structures. And then we can set up a lineup, but being able to create null plots is really key. So yeah, that's a great question.
Okay. I don't know whether there are some more questions. I don't see anything more in the chat, neither on the question and answers section. If not, it's 1:27, so we are exactly in the time slot of 60 minutes. So if not, I would like to thank you on behalf of all the audience. It's actually a very nice idea with both a theoretical foundation as a practical impact. So thanks a lot for your time, for your energy to share us this work. And we hope one day to see you here in CIMAT. First, well, we have a pandemic problem to be solved. Well, first of all, we have a Facebook and WhatsApp problem to be solved, and then other problems. Yes. Okay. So yeah. Good. Thanks again. And we switch to Ricardo, because Roland has an announcement about the next seminar.
Thanks so much for having me.
Thank you, Professor Hofmann. Just a short announcement. On October 18th, we're having another conference of Professor Lane Harrison from Worcester Polytechnic Institute. The conference is Quantifying the Individual Experience of Visualizations. It's 12:13. So we're having at the same time this conference. Please follow us. El día 18 de octubre a la misma hora, 12:30, tendremos la conferencia de Lane Harrison, profesor de Worcester Polytechnic Institute. La conferencia es Quantifying the Individual Experience of Visualization. Los esperamos a todos y muchísimas gracias, profesora Hofmann, por estar aquí con nosotros y por compartir sus conocimientos. Hasta luego.